Yeah, that's your. Okay, we're official now. Okay, well, so for anybody who hasn't had the pleasure of meeting her already, or seeing her at the myriad journal clubs, Gemini North journal clubs that she's presented at, this is Lu Shen. She's visiting from Texas A&M University. Lu got her graduate degree at UC Davis, working with myself and Lori Lubin on radio, radio AGN, radio galaxies in what was at the time high redshift clusters, which is now low to intermediate redshift clusters. So redshift 1 clusters. And I think you put out like 4 papers as a grad student, all on AGN in different groups and cluster environments. She then went to Haifei to do her first postdoc, where she worked on a variety of different AGN physics mostly. And then now at Texas A&M, where she's pivoted to galaxies, to the correct side of the universe, working mostly from the perspective of GWST, NG and Sears and Capers. So she's going to talk about some of that work today. So please, Luke.
Thanks. Okay. I just thank you, Brian, for the great introduction, and I would just start talking about my science. So today, the topic is galaxy evolution at cosmic noon, and most of the work are done in like spatial resolved way. So this is something from spatial resolved star formation, and the project I'm going to talk today mostly are based on NGDeep data. So I put up most people from NGDeep collaboration and some from Sears. So talking about galaxy evolution, so this is a very huge topic from the large scale structure all the way down to the central black hole. And I just want to briefly go through some of the very quickly the idea of galaxy evolution. So the galaxy will the gas from the large scale structure will feed the galaxy, and then the galaxy will have star formation and AGN activity, and this process the galaxy grow. And then because of the intense star formation and the AGN activity, they also eject the gas out of the galaxy, and this will remove the gas and lower the star formation. And some of the gas will cool and come back to the galaxy and start new star formation and AGN activity. But as long as this process goes, the dominant will change, and then the galaxy eventually will become a quiescent galaxy. So this is like that. So one of the key problem question we have is how the galaxy quenching. So we know that star-forming galaxies are disk dominated and they're more extended, and the quiescent galaxy are both dominated, as shown here, and more compact. So here is a plot from Vanderbilt 2014, and this is the size of the galaxy as function of stellar mass. And you see as fixed the stellar mass, the star-forming galaxy, the blue dots are higher, larger than the quiescent galaxy. That's showing as the red dot. And this difference and the trends here is sustained from redshift 0 all the way to redshift 3. At the point we have the HSD data, and this is rest frame 2000 angstrom. And with the GWC, we also find the similar trends with star-forming galaxies more extended than the quiescent galaxy, and extend to a higher redshift and also at rest frame 1.5 micron. So this is suggesting that as galaxy quenching, grow and quenching, they have some structure changes as well. And So one of the way to understand how the galaxy quenching, we think it is also important to study the spatial resolved star formation and the spatial resolved physical condition of ISM. So how galaxy are like the quenching is propagates within the galaxy. Then we go like this is a part of the goal with this survey, and this is the NG Deep survey, and we have nearest and near cam imaging together in parallel. So the nearest is looking at emission line the emission line properties in galaxies. For example, the O2, O3, H alpha, H beta, and down to very low stellar mass, like 10 to the 7 to 10 to the 8. And this is for the nearest is on the Hubble Ultra Deep Field in good south, so that it already have a lot of data to back up. And then the near cam part is focus on the region we have like very deep HST FA14 imaging. So combining the near cam imaging, we could do like discover and characterize property for like galaxy at above 10, redshift 10. I'm not gonna talk about this part. So this is another mostly Steve Finkelstein is in charge of that part of study. And today I'm gonna only talk about the nearest part. So here is a like stacking spectrum for the nearest, and you can see the O2, O3, H alpha emission line, a function of the redshift. And on the right, I'm showing the reconstructed line map. So the first one is the false color imaging, and then the H alpha. And the bottom is also showing some emission line maps, O2, O3, and H alpha for the galaxy. And we reduced the NGDeep nearest data using the Grizzly. It's very kind of powerful pipeline that we have. We didn't use the official one, but this is a very good one because we can do SED fitting together and get more results like here. So here showing this is the SED fitting. So we only get this part of the spectrum, but we can add the photometry with at blue and the rider band to have a full SED fitting along with the spectrum. And so on the top is the 2D spectrum from 4 positioning angle. And on the bottom is a combined 2D with continuum, modeled continuum subtracted. So we only get, this is highlighting the emission lines. And on the bottom, this is 1D spectrum with the photometry fitting. And this is the fitting for the spectrum. And then the last one is just the redshift P of C histogram. And with the 4PA, 4 position angle, we have more information to reconstruct the emission line map in 2D. And here is showing like the O2, H beta, O3, and H alpha maps. That's the same actually, it's like previous slides. Okay. So with this data, the first study I did is to study the spatial resolved star formation. And we select for this, this is using the half data set that we observed in the first 2023, early 2024. And this is a sample of 19 star forming galaxy between redshift 0.6 to 2.2. And we measure the equivalent with H alpha maps using the Grizzly. And here showing the star formation rate versus stellar mass scatter plot for those 19 star-forming galaxies. So they're mostly on the main star-forming main sequence. And then on the right, I'm showing the full color imaging and along with the H-alpha emission line maps. So with the H-alpha emission lines, we could do equivalent with H-alpha. So this is H-alpha versus the continuum, and we subtract that, that's the H-alpha emission line, equivalent with H-alpha. And on the bottom two, that's the specific star formation rate map and age map. And those are obtained from single ICD fitting with some binning to get to increase the signal to noise of each binning with the photometry from HST and the GWST. And also with that, we could do a gradient. So we calculate, like for example, here is showing the equivalent with H-alpha as function of radius, and we measure the gradient of that. This is another way to say, like I will show next. So we first compare the gradient of specific star formation rate and the equivalent with H-alpha gradient, and we see like there's like most of galaxy have positive H-alpha equivalent with gradient. This is consistent with the inside out quenching that people also find using the HSC data. This is the size of H-alpha and the size of continuum as function of stellar mass. And this is showing the H-alpha emission line size is more extended, and that's the galaxy has a still have higher star formation on the outskirt and the outskirt of the galaxy. And also here, this is a result from Petrella 2018. And you can see the, I believe this is the star, the H-alpha emission line, and then the bottom is a different it's the right one is more massive one, and this is less massive galaxy. And also we see the galaxy, we color coded the galaxy with a star formation rate. The difference between star formation rate and what's supposed to be the star formation rate if they're aligned on the main the star forming main sequence, and the galaxy with higher star formation rate, those are like yellowish, orangish color. They favor like negative gradient. So, and we also see in the imaging they're likely having some merger or starburst that happen in the center. So those galaxies are favoring like more negative gradient. And we also see here is the equivalent with H-alpha gradient is correlated pretty well with a specific star formation rate gradient. But we also see that there's a large scatter here. And with the data, we can also do like pixel to pixel comparison between the equivalent with H-alpha and the specific star formation rate, and also with the age. And on the left, I'm showing here the equivalent with H-alpha versus specific star formation rate, and the blue are the like 2D histogram of this comparison, and on the right is equivalent with H-alpha versus the mass weighted age, and also like the 2D histogram. And the small dot, like the red cross, those are individual like integrated emission for each galaxy. And this line here is result from most diff is also integrated emission. So what we see is like we generally see like the result are consistent with the what they found in the integrated flux of galaxies, but we also see there's a kind of like offset, like bend trend, like at lower specific star formation rate. This end, and like this is bended, like, but we don't see that bend in the integrated version. And also another thing is we see there's a large scatter than the integrated relation. So this is like one sigma from the integrated result, but we see a larger scatter.
Might I ask you a question?
Yeah.
So what do you think drives the bend and what do you think drives the scatter? Because I mean, taken at face value, the specific star formation rate is the equivalent width of H alpha, right? Because you're just equivalent width of H alpha is just the H alpha flux normalized by the continuum, and that's basically what a specific star formation rate is. So those two quantities should correlate really well with one another, but
One thing that is not correlated very well is one is based on shorter time scale and the specific star formation rate. I'm using here, I didn't mention, is average over 100 meg a year. And the H alpha is usually 5 to 10 meg a year. And the difference between this is the causing, we think, for at least the large scatter we see here. But we don't know the band if it is like the sample we have and the integrated have like could be like tilted to like lower mass part, like low star formation or high star formation rate part. And then also because of the question you asked, and we go to look at why there's a large scatter in that in the comparison, and we compared with the like simple delay tau star formation history model, and with different tau and different age we plotted here. It's a little busy plot, but this is like, for example, you see this one is 8.2 gig year, and with the different color on the tau the tau model. So the darker is more sharper, like it will quickly the star formation will quickly decay, but with like going this way, it's more like steady star formation history. And we mostly cover, like our 2D histogram is mostly covered by this plot. And what we see is then we also bin our galaxy depends on the location to the center. So this is like the radius versus effective radius of galaxy within 0.5 and then 0.5 to 1 and 1 to 1.5. And we see there's a trend as like this. And that means like outer skirts, it prefer more steady star formation history, and then the center is more is prefer like shorter tau model like bursty. And so this is the result, like we think the central region of the galaxy, for like the bulge, they form like in a rapid star formation episode, but the outskirt, like more or less the disk of the galaxy, will grow in a more steady star formation. Okay, that's for this project, and then I may pause a second just for question. Okay, and I will continue. So we know that star formation is a key driver to the galaxy evolution, the galaxy growth, like and evolution. But also the star formation is tightly correlated, with the ISM properties, because the ISM is the fuel for the star formation, and some like ISM properties like density, metallicity, and ionization state, they all affect how the galaxy, like how efficient the star form. And also in the meantime, the interaction between the newborn stars and the ISM will affect the both sides, like the star formation and the ISM properties. So here I'm mostly talking about two main ISM properties. So this is metallicity and the ionization parameter. So usually people use like metallicity, like they are traced by O3, O2 versus H beta. This is not direct method. This is strong, strong line measure the metallicity. And here I'm showing metallicity as function of stellar mass, and you see this is the like mass metallicity relation. Like they are correlated very well. And also on the right, I'm showing the ionization parameters that's traced by O3, O2 ratio as function of stellar mass. And you see at higher, like both a high redshift and low redshift, they have a very well correlation with the stellar mass. But one thing you may notice, we don't know anything about redshift. For galaxy of low redshift, like below stellar mass of 9, and this is because we don't have the ability to observe this region. But this region is very important because as we go to higher redshift, most of the galaxies are in this region. And here I'm showing results from recent JWST data. So here is the metallicity as function of stellar mass. And also here, this is also metallicity versus stellar mass. And you can see based on like early results, we see there seems like there's a banded, like shallow relation in the metallicity mass relation than what we see in the previous results, even at similar redshift. So this is the similar redshift result. And the NGD data is really a way to, we think, to bridging the low redshift and high redshift difference. So here is again O3O2 ratio as function of the we call R23, so O3 plus O2 versus H beta. This is a trace of metallicity, and this is SDSS at redshift 0 and most stiff like previous observation for redshift 2 to 3 galaxies. And then we have the NG deep that's dominated in this region, plotted in the purple pink squares. And then the JWST high redshift galaxy in the diamonds, in purple diamonds. So our galaxy are in the like a region that connect the both low redshift and high redshift. And on the right, I'm showing the number that's the stellar mass histogram, and you see the NGD are tilted to lower stellar mass and also extend to the region that mostly high redshift galaxies are recede in.
Can I ask just like an observational question? Why did MOSDEF not target these objects? How, like, what's their typical, let's say, H-band magnitude?
No idea.
But they're super faint.
They're faint.
26, 27 or something like that.
Yeah, 26 at least. Yeah.
Okay.
Something like that.
So that explains why they didn't target them.
Yeah.
Okay.
Yeah, I feel like most have some galaxy like 10 to the 8, but not like a lot. And they have like mass completeness saying usually they say at 10 to the 9. Yeah. And okay, yeah, for and then we go like 28-ish magnitude. And then we for my the talk I'm gonna the project I'm introduced later is mostly on the O3-2 ratio, the ionization parameter first. And then we select some galaxy that has O3 and O2 measurement above signal to 5, and we here those galaxies, and we have like stellar mass down to the 10 to the 7 solar mass, but we think that our mass completeness is like 10 to the 8.5. And here is showing the galaxies in the star formation rate mass plot, and they're mostly slightly higher than the main sequence. And this is because what we selected are emission line galaxies based on our method. And on the right, I'm showing the O3 versus O2, the O3 O2 ratio as function of stellar mass. And we see a very well correlation all the way down to very low stellar mass. And this is we only fit our derive this relation down to like our mass completeness 10 to the 8.5, but we see this correlation remain as the lower stellar mass galaxies. And then we also did that for specific star formation rate and the specific star formation rate. Because we see difference in the star formation rate plot, so we separate them based on the redshift and the color by orange for the higher redshift galaxies at redshift 3, and the purple one for the slightly lower redshift at redshift 2. And we see negative trends with the star formation rate, but also like another positive trend with the specific star formation rate. And also we compare this with the SDSS low redshift galaxies and some like purple, some blue greenish galaxy for the blue dots, green peas, those classy galaxy, those are considered as high redshift analog. But at redshift 0. So our relations are more consistent with those analog results, but very different from the normal local galaxies from SDSS. Yes. Okay, and then we see I show in the front like there's a very strong mass metallicity relation, and what we see here the O3-2 ratio as function of stellar mass, which make us thinking about could the metallicity be a dependence, the main driver for that relation. And here I'm showing the O3-2 ratio as function of ionization parameter. This is from photon ionization model, and you see like the different color trend are for different metallicity. So metallicity really could affect the O3-2 ratio and like how they translate to the ionization parameters. And we use the IZI it's a code based on photon ionization model, so it will tell you what you gave the O3, O2 like H beta, H alpha measurement. It will return you what the best fitted ionization parameter and metallicity is. And here I'm showing here the ionization parameter as function of O3-2 ratio. And on the right, that's the metallicity versus O3-2 ratio. And what we'll see is the ionization parameter correlated better with the O3-2 ratio. And the metallicity is correlated, but if there's a very huge scatter and with large error bars. And so we think the ionization parameter is the dominant trend, dominated in the O3-2 ratio relation we see. And then we then consider like what's the ionization, what part of the ionization parameter that could affect our O3-2 ratio relations. So ionization parameter is mainly correlated with the ionizing photon production rate, the Q, and the number density of hydrogen as the N sub H. So here we use an equation that the ionizing photon rate production rate is correlated with the H alpha luminosity, and that's the plot on the right top. So the ionizing photon production rate as function of O32 ratio, and because the H alpha luminosity is similar to the star formation rate, and this is the relation that we also see in the star formation rate versus O32 ratio. So this is a negative trend, and that's why we don't think the Q will be the dominant reason for the O32 ratio to like changing of the O32 ratio. And then we also consider the ionizing photon efficiency. That's usually called the psi-ion. That's the production rate versus the UV luminosity. And on the bottom, that's the psi-ion as function of O32 ratio. And we see a very like clear positive trends there. And again, if you consider the Q is as H alpha, that's what we calculated. This is similar to the H alpha versus UV luminosity. And this is also used as like a trace for the burstiness, or if there's a reason to enhance the star formation. So what we think the reason to enhance star formation or the reason burstiness will affect the O32 ratio. And then we also consider the number density of hydrogen. We don't know the number density of hydrogen, so we use a relation to like to propagate that. So we use the star formation rate density because it's correlated with the molecular gas density. And here on the right, I'm showing the O32 ratio versus the star formation rate density. And the density we calculated is star formation rate versus the effective radius we measure from 606. That's the red frame UV. And we as a proxy for the size of the star formation rate. And we see a positive correlation, but with a very large scatter of 0.5 DAX. But we still, like in this paper, we conclude that both the enhanced star formation, recent star formation activity and the higher star formation rate surface density may contribute to the increase of O32 ratio and also the ionization parameter that we see in the high redshift galaxy compared to the low redshift galaxies. But also I want to mention that both of them we see here this efficiency and also the later the star formation rate surface density has a large, huge, like large scatter. But then we try to look at what the spatial resolved ISM properties. So here I'm selecting 50 star forming galaxy from the 100 to almost 200 galaxies. Because of the you need enough pixels to doing any spatial resolved studies for galaxy at low stellar mass, like this part. They're small, they're compact. We don't have enough information to do any spatial resolved study. But we could do for galaxy at like 10 to the 9-ish solar mass. And here on the top is O32 ratio map with dust corrected, that the dust correction is made with SED fitting on the photometry. And the second column is the stellar mass surface density, and on the bottom is the star formation rate surface density. And I just want to highlight one thing we see is what we have measured on the O32 ratio, and we also have a higher star formation rate surface density. But this is not seen in the stellar mass surface density. So this is suggesting there's a very strong correlation between the O32 ratio and higher star formation rate surface density. Even though we see like the integrated version, the plot, we see there's a large scatter, but in the resolved way, we see a strong correlation there. And we also try to measure the gradient for those properties, O32 ratio, stellar mass, star formation rate, and specific star formation rate. The gradient as function of radius. And we plotted the O32 gradient as function of stellar mass gradient, star formation rate gradient, and specific star formation rate gradient. And we calculate the p-value of whether they have like a correlation. And we see the O32 gradient is positive correlated with star formation rate and specific star formation rate, but not with stellar mass gradient. And this is consistent with what we see in the previous slides with the map, the surface density map. And we also did the pixel to pixel 2D histogram for the O32 ratio as function of the star formation rate surface density and the equivalent width of H alpha. That's the kind of specific star formation rate. And we see both a positive correlation there. And this is suggesting that both the enhanced star formation activity and higher star formation rate surface density may contribute to the increase of O32 ratio and then the ionization parameter. But this is result consistent with we find seen in the integrated version, but more clear and like more significant. Okay, that's my summary. So we have like JWST, very good JWST data from NEAREST that allow us to do spatial resolved study on galaxy for high redshift, like redshift above 2, and we could do spatial resolved with a kiloparsec scale. And we study the equivalent with H alpha maps, and we also study the physical condition of ISM, the metallicity. We didn't do metallicity in here, but we're gonna do that later. We did the ionization parameter, and what we see is we see the O32 ratio, the ionization parameter is correlated, integrated with stellar mass, but internal spatial resolved way, the enhanced star formation rate and the star formation rate surface density contribute most to the O32 ratio, the change of ionization parameter. That's it. Any questions?
Questions? No? In the room or online? Good, please.
Thanks for the interesting talk. Trying to digest.
Oh, sorry. Maybe I talk a little bit fast.
So I was just wondering, I'm not sure if that question really makes sense, but so I was wondering if you're considering like the classical BPT diagrams. I assume most of these star-forming galaxies would end up high in terms of like more or less like the AGN almost type of the diagram, right? Which is what has been always proposed for high redshift. Because they have a much higher ionization parameters, I guess that would be out of the low redshift star forming region and more like driven into this AGN type region in the diagrams.
Firstly, the data do not allow us to do those things because like at least the H alpha and the N2 are blended. So you may notice sometimes I wrote the H alpha with the N2 like in the plot because they're blended, we cannot resolve them. So for the typical BBT diagram, we cannot do that. But we also try on some like some of them also has sulfur two, but not all of them because the wavelengths we cover is quite short for our nearest data we have. We see we only did those like we tried this for some galaxy and also galaxy with high ionization parameters with a high O32 ratio, and we don't see there in the AGN set part. There's still like a star forming part. Even for those like very high O32 ratio galaxies.
But
So-
it might be due to uncertainties.
Yeah, it could be like uncertainties, it will shift. But another thing we noticed for those higher O32 ratio galaxy is they have very weird dust property, the H alpha versus H beta of them is very weird. The like zero, like negative-ish, like below 2.86, so below the case B case. So that we there's something going on in those kind of galaxies, and we don't know, and particularly the dust properties. Yeah.
Okay, thank you.
But it's the case that case B is not working for a lot of galaxies in JWST, right?
Yeah, yeah.
This is not common to this sample or some systematic. There's clearly something going on with these types of galaxies.
Yeah, one of the thing that happened in that paper is we were trying to correct the dust because the O3 and O2 they also like you need the correction on the dust, and we try to use H alpha versus H beta, and then we see there are a lot of galaxy that like the case B couldn't make sense. And we see there's a strong correlation with O3 H alpha versus H beta as function of stellar mass. So because previous studies we stop at like 10 to the 9-ish galaxies mostly, they don't see the like lots of galaxy has these problems, but with like the lower stellar mass galaxy, we see this is most of them are having this like violation to the case B.
Right.
Yeah.
But you're specifically picking out high SSFR galaxies.
Yeah, that's
this, so
another.
That's a very peculiar part of phase
Yeah,
space.
that's also another thing that could affect like this.
Yeah, because you cut on the emission line equivalent width, right? And so you're naturally going to Malmquist bias into getting
Yeah,
these types of galaxies.
yeah.
We have plenty of time for other questions. If they'd like to ask. Do you have UV spectra of any of these galaxies? Rest frame UV? It's in a pretty famous extragalactic field, so I imagine
Muse. Is Muse gonna give us UV?
It's in HUDF, so
Muse.
they have.
Yeah, so those 30-hour views
UV
there.
candles.
Yeah, UV candles is not a spectrum, it's only the photometry.
And you can obviously you can cover like from like continuum to M alpha and from 900
9,000 900. Yeah.
rest for 900.
I was more wondering about like carbon-4 and carbon-3 and helium-2 because these things are sitting in a fairly peculiar part of the traditional BPT diagram. There's this idea that you can pick up these types of systems in the UV as well using carbon-4, carbon-3, and helium-2 BPT like diagnostics. And I was wondering if, especially since there is very deep news in this field,
Yeah,
if you tried to correlate or anybody's tried to correlate that.
No, nobody tried to correlate that for now, but it's definitely doable. I don't know if muse are deep enough to pick up all like low mass galaxies, but like probably okay for like the galaxy like not so faint. Yeah,
I mean,
and also those galaxy, because our selection, they're also like emission line galaxies, so they should be maybe okay.
yeah, this is
Yeah.
exactly what Muse is great at too, right?
Yeah.
Picking up these emission line galaxies
Yeah.
that don't even have continuum counterparts.
Yes, yes.
Within this kind of comparison for average galaxies, we find like UV diagnostic diagram can not like distinguish between AGN or star-forming galaxy. I think Muse team had already done a lot of UV diagnostic with their archive data, and same conclusion cannot distinguish. And recently, we have a collaborator, Nico Clary. He who was a graduate student from Texas A&M. They run a lot of cloudy model with input, I mean, star-forming galaxies and AGNs. They test both UV and classic optical BPT diagrams. They find nope, cannot distinguish between star-forming and
Yeah.
So yeah.
That was my suspicion. Any last questions? Or online? If not, let's thank Lou again. Thanks everybody for coming.